Hi, good morning. Okay, so here we go. Um, uh, so we had a bunch of lectures on linear algebra. We did a bunch of stuff on linear algebra, and basically now what we're going to do is all that stuff we did on linear algebra, we're going to look at a particular vector space, namely the tangent space at a point x to a manifold, and we're going to do linear algebra in that vector space. And again, mostly it's about notation. And so last time we ended the lecture by thinking about a particular basis for the tangent space. And so the setup is that you have a manifold with a chart and it has coordinates. And then you define a basis, a basis. And the basis we denoted by these funny sort of symbols for a basis. And again, this all kind of rationalizes, the notation rationalizes, but not quickly. So you're just gonna have to stick with the kind of funny partial derivative notation for basis vectors. And then we'll see why it makes some sense. And so the way we defined this basis was so we have a chart, okay, and the chart therefore has associated to it a natural chart for the tangent bundle, and remember we had notation for that. Okay, and so all we do is we take these tangent vectors, and we say that they get mapped to the standard basis vectors for Rn under the coordinates t phi for the tangent bundle. Okay, so writing that all down, it says this. It says that t phi, okay, so the tangent bundle coordinates for the jth basis vector, okay, is, well, in the first component, of course, it's going to be x, or the coordinate version of x, which is phi of x, and then the vector is ej. Remember, this is the jth standard basis vector. Okay, so that's where we got to last time, and so you know, as I said last time, there's going to be a homework problem to show, in fact, that the tangent space is a vector space. But you know, accepting that, if you make this as your definition, then this is obviously a basis, just because the standard basis vectors obviously form a basis. Okay, and you know, this kind of maps, you know, bijectively, and so this maps each of these uniquely onto one of these. And so you have a linear map that maps a basis onto a base, a set of vectors onto a basis. So that set of vectors must itself also be a basis. Okay. So that's the basis for the tangent space. Oops. Now we're going to talk about an important concept which comes up in multiple different ways, and we'll see some of those as we go along. So a vector field on a manifold M is a mapping, and I typically write a vector field by capital X. So it's a mapping from M into Tm, okay, that satisfies that if you evaluate the vector field at a point x, so we know that that gives you a tangent vector somewhere, right? Because it takes its values in Tm. But the point is that if it's a vector field, it doesn't just give you a tangent vector somewhere, it gives you a tangent vector at x. Okay, so in other words, very simply, it assigns to every point in M a tangent vector at that point. Okay, and so a vector field is of class CR, and here R is okay, so it's R times continuously differentiable. So R could be 0, 1, 2, all the way up to infinity, 0 meaning continuous. Okay, so vector field is of class CR if X is a CR, well, use the class CR mapping. Right, and the point is that that terminology makes sense to us now because we defined what it means for a mapping to be of class CR. Okay. Okay, so maybe let me first draw a picture of how you should think about what a vector field is. Well, a vector field is, kind of literally, a field of vectors. Okay, so if this is M, what it says is that at every point you have a tangent vector. Okay, so if this is the point X, this is the tangent vector X at X. Okay. So that's how you can visualize a vector field, and being of class CR just means how nicely these things fit together as you go from point to point. All right, we're going to be very concerned with how to represent vector fields. Okay, and by representing, I mean representing in a set of coordinates. All right, so first of all, we have a manifold and a chart. And I name the coordinates X. Okay. And so remember that, so X is X1 up to Xn, these are just the labels you use for the coordinates. So for example, it could be polar coordinates, Cartesian coordinates, spherical coordinates, X, Y, Z, R theta phi, stuff like that. Okay. All right. So first, note that we have a vector field. We have vector fields. D by dx1 through d by dxn on, not on all of M, because these vector fields are only going to be defined on the domain of the chart. So these are defined on U. Okay, and they satisfy, this formula. Okay, so that looks like I just wrote something stupid, but it's not quite that way. So remember, this is the basis vector for the tangent space at X that we talked about above. This thing is a vector field, and so here I'm evaluating that vector field on X, and the fact that this equation looks stupid just means that I made a good choice for how to call that thing. Okay. All right. Okay. So maybe just to sort of drive that home, how you can think about that. So here's my manifold again, and now I have a chart, U, and a chart map, phi. Down in Rn. And so what I know is that down here in the codomain of the chart, I have the standard basis vectors, and I can think of these as being, attached to one version of these at every point. So let's say E1 and E2. And similarly, at this point, I'll have E1 and E2. All right, and you have these at every point in phi of u. Okay, now corresponding to that, up here, you're going to have corresponding tangent vectors d by dx at every point. Okay, and so you'll have like something like this, and over here something like this maybe. Okay, so this will be maybe d by dx1 and d by dx2, d by dx1 and d by dx2. All right. All right, and so you'll notice that here I've sort of drawn these as orthogonal, and that makes perfect sense because here I'm down in Rn, and Rn has an inner product, and these things form an orthogonal basis with respect to the standard inner product. Up here, there's no notion of orthogonality at all. There is no standard inner product on the tangent space of a manifold. What is true is that if you choose a set of coordinates, the inner product down here gives you an inner product on the tangent spaces up here, but it's not natural. It depends on the set of coordinates that you choose. And what we're going to see is that we're going to definitely have inner products flying around, but they're generally not going to be the standard inner product for Rn. Those inner products are going to have physical meaning. Okay. All right. All right, so now we have this these basis vector fields, and so therefore, if I have any vector field, let's say capital X, at every point in U, x of x will be necessarily a linear combination of the basis vectors at the tangent space to x at the point x. Or, sorry, tangent space to M at the point x. Okay, so if x is a vector field, okay, we can write x of x equals, right, so let me just sort of first say that because it's a vector field and because this is a tangent vector at the point x, it's necessarily going to be the case that this thing will be a linear combination of the basis vector fields at the point x. And the coefficients in the linear combination, we're going to write as x super j. Okay. So these are called the components of x in the chart U phi. All right. So another way of saying exactly the same thing is to write the local representative of the vector field. Okay, so x, the vector field is a mapping, right? So it's a mapping from M to Tm, okay? And I have a chart for M, which is U phi, all right? And I have a chart for TM, which is TU, T phi, all right? And so it makes sense then to say, what is the local representative of X with respect to these two charts? Okay, and it's determined by these components that we just wrote up here. Okay, all right. So the is to write the local representative of X, and this is. Okay, so let me just sort of write this in the notation that we use for local representatives, right? So if I had a local representative of a mapping F between two manifolds which had charts U phi and V psi, well, we talked about this, then we wrote the local representative like this, okay? But now, F is X, phi is phi, and psi is T phi, right? And so it's going to be X of phi T phi, okay? And so this is going to be a mapping from phi of U into phi of U cross Rn. Okay, so this is the local version of M, and this is the local version of Tm. Okay, and what will that thing look like? Well, it's going to take a point down here, which is just going to be some vector in Rn, and I'm going to write that as a vector as an X with, and again, I'll put a little bar under it just to make sure we understand that that's a vector in Rn. And so this thing is going to map to, okay, well, just by virtue of the fact that a tangent vector has this property. Okay, so it maps X and gives me a tangent vector at X. In the first component of this local representative, it's going to be the identity. Okay, and then here I'm going to get X1 of X and Xn of X. Okay, and so these are, again, the components of X. Okay, so that's sort of two ways of representing a vector field. One using the basis notation, okay, like this, okay, and then the other using chart notation, like this. Right, they're equivalent representations of the same thing. Typically for doing computations, this is the most compact way to do things, as we will see. Okay, so that's what vector fields are. Okay. Okay, let's look at the change of basis formula, which really comes in this case from change of coordinates formula. So really what we're going to be doing is we're going to be looking at the overlap map for the tangent bundle, but now we're just going to have sort of enhanced notation for that. And the notation is going to arise from exactly the fact that it's going to be convenient to write tangent vectors in that kind of notation. Okay, so the point is, this is extremely simple. It's just doing something we've already done before, which is the overlap condition for tangent bundles, and it's adapting that to this notation. That's all that we're doing here. Okay. So the change of coordinate formula. For vector fields. Okay, so remember what the overlap map for the tangent bundle does. Well, so maybe let me explicitly write it down. Okay, so let's say we have charts. U phi and U tilde phi tilde. And they overlap, if that kind of goes without saying, because if they don't, then there's nothing to say. And the different coordinates we denote by x and x tilde. Okay, and then the overlap map. For TM is, okay. So it's x bar. So again, I'll write bars under things just to emphasize the fact that these are points in Rn instead of points on the manifold. So it's phi tilde composed with phi inverse of x bar. Okay, so it's in the x component, it's just the overlap map for m. And then in the v component, it's the derivative. Okay, so it's d of phi tilde composed with phi inverse evaluated at x bar. Okay, so this thing is, the Jacobian. So this we acknowledged was an n by n matrix. Okay, and this gets applied to the vector v bar. Okay. If v bar, is x of x bar, and maybe let me write it out in full components, x1 up to xn. Okay, so these are the coordinates, of course, in the these are the components of x in the untilde coordinates. Okay, but we're also going to have the components of x in the tilde coordinates. Okay, so let me just sort of emphasize here. So this up here will be, x tilde, and this up here will be v tilde. Okay, and so then the way this formula reads is it reads that x tilde is the Jacobian times x. Okay, and so I'm just going to write that now using our, we spent all this time talking about linear algebra and summation convention. So I'm going to, use that way of representing that kind of linear map, which maps v into v tilde with the corresponding linear map being the Jacobian. And the way you write that in components using the summation convention is that x tilde j is d x tilde j by d x k x k. All right, because after all this is, okay, is this just a so all this is that it's a representation of x tilde in terms of x, okay, and then all this is it's the partial derivatives of x tilde with respect to x, just exactly like I have here, okay, and so this formula here is simply that formula there. Okay, so this is the change of coordinate formula for vector fields. Okay, So if you have a vector field, it tells you how the two different coordinate representations on overlapping charts, how the representations are related. Okay. Now, what this does is it gives you a formula for how the components of a vector field are related. But you could also wonder, what's the relationship between the vector fields, the basis vector fields, the partial derivative things, okay? Okay, so one also has a change of coordinate formula for the basis vector fields. Okay, and from linear algebra, you know how this goes. So usually in linear algebra, you do it the other way around. What you do is when you write the change of basis formula in linear algebra, you don't start with the change of basis formula for the components of a vector. You start with the change of basis formula for how the basis vectors are related to each other, and then from that you deduce this. But of course, that process is invertible. If you have the formula that relates to components of a vector in two different bases, you also have the formula that relates the basis vectors themselves, okay? So we're kind of just doing the process that you usually do in linear algebra. We're doing that kind of backwards, okay? But I'm just going to kind of give you the answer here, okay? And so what you want to know is you want to know how is the basis vector field, d by dx tilde j, how is this thing related to the basis vectors in the untilted set of coordinates, okay? So you're going to have, it's going to be some linear combination of the other basis vectors. And so I'll index those by a k because it can't, all I know is it can't be j because I'm going to have some linear combination involving k. So, and so the thing is, what goes in there? Okay, well, it's going to be if you think about the way the change of basis formula works, if you have a matrix that relates the basis vectors, the matrix that relates to components is the inverse. Okay, so what we're going to get here is we're going to get the inverse of that. Okay, and so the inverse of the Jacobian is the Jacobian of the inverse, right? So, you know, here I have that this is the Jacobian of the overlap map. And here I want to, you know, write down the Jacobian of the overlap map that goes the other way. But that's just going to be, instead of being dx tilde by dx, it's going to be dx by dx tilde. Okay. So it's going to be dx by dx tilde. Okay, and all that remains now is for me to put indices on that. And to put the indices on that, you just, you know, one way to think about where the indices should go is that you sit down and you work it out, right? So you, you know, you use the fact that the relationship between the components looks like this, and then you go back and you look at how the component matrix is related to the change of basis matrix, and you work all of that out. Okay, so that'll take you a little while. Or you just trust that the summation convention works and you put the indices in the only place possible. So, of course, those two methods give you the same answer, or else I wouldn't have even suggested the second one. Okay. And so I have to have a free j on each side, and it has to be the same thing on each side. It has to be either a superscript on each side or a subscript on each side. And in this case, it's a subscript, meaning seeing as it's a superscript on the bottom. And so the j has to go there. I cannot put it there. So, you know, you just sort of blindly follow the summation convention. And so if I put the j there, then the k has to go here, and, you know, lo and behold, the summation rules work. I have a superscript here and a subscript here. Okay, so the summation convention is designed to help you write down formulas like this. Okay, so this is the change of coordinate formula for basis vector fields. Okay. So here's something you can try at home. X tilde j d by dx tilde j is equal to x j d by d xj. Okay. So just substitute in everything here, right? So substitute in x tilde from there, substitute in d by dx tilde from there, plug all the stuff in, and so it's a little exercise in using the summation convention to show that this holds. And this just simply means that this and this are just coordinate representations of the same vector field, which of course they are. Okay. All right. Now, why am I obsessing over this business about change of bases and change of coordinates and the specific form of the change of basis formula and stuff like that? Okay, why does that concern me? Okay, the answer should not be immediately apparent to you. Okay, so in other words, there's some questions that I ask you, and there's kind of only one possible answer to that question. It's sort of like if I ask you to, sort of what are the possible values for this number? There's only three choices: 0, 1, or infinity. It's not going to be 17. All right. But this is a question which kind of does not have an obvious answer. Okay, but it's an important answer nonetheless. So I'm going to tell you what the answer is, and it kind of won't make sense, but we're just going to immediately look at an example which illustrates the thing that I'm talking about. So the change of coordinate formula can be used to identify what sort of geometric object we are dealing with. We don't have many geometric objects in our toolbox right now, so this answer lacks context for you. The only geometric objects we kind of know about a little bit are manifolds, mappings, and vector fields. So, but we're going to be talking about other kinds of geometric objects. So let me immediately illustrate what I'm talking about with an example. Okay. So there's a thing that you know about. So let M be a manifold. And F a smooth function. So in geometry, typically when you say function, you mean a scalar valued thing. If it's not scalar valued, you often will call it a mapping or a map or something like that. So function means scalar valued. Okay, let's define the gradient vector field of f by requiring that if x1 through xn are coordinates for m. Okay, so now I'm, for the first time, I think, I'm using a shorthand, which is very common. So prior to this point, I've been sort of careful, I think, about saying whenever I introduce coordinates, I say I have a chart which has coordinates. Okay, very often you just skip over the specific u phi and you just say I have coordinates. Okay, so what this really means is this is just short form for I have a chart u phi with coordinates that I'm going to call x1 up to xn. Okay. Okay, so I'm going to define the gradient vector field of f by requiring that if I take any set of coordinates for m, the components and so the gradient vector field of f, I'm going to denote it by the usual way that you denote the gradient vector field, grad f, okay? And so I'm going to define grad f. They're going to be the components of grad f, the ones that you're used to. Okay, fine. Okay, now, is that actually a definition? Okay, and so what do I mean by that? Well, I'm telling you that I'm defining a vector field called the gradient vector field, and I'm defining it by telling you what it looks like in coordinates. Okay, so then the question is this definition, does this definition make sense? So in other words, if I were to choose a different set of coordinates, let's say x1 up to xn tilde, would the components of this vector field grad f assume the same form in that other set of coordinates? So does this definition make sense? I.e., if x tilde 1 up to x tilde n are other coordinates, are the components of grad f equal to df by dx tilde 1 up to df by dx tilde m. Okay, perfectly legitimate and a well-formed question. And moreover, the change of basis formula gives me a way to answer this question, because it tells me that if I have a vector field and I have two different sets of coordinates, the components of the vector field must be related by that formula. Okay, and so the question amounts to, is it true that the components of this vector field, which are the df by dx's, are they related in the proper way to the df by dx tildes? Okay. So this amounts to verifying whether the change of basis formula is satisfied, or the change of coordinates formula is satisfied. Okay, so what does that mean? So that just means exactly this. Okay, except x here is replaced by the partial derivatives of f with respect to the coordinate functions. Okay, and so that means that I should verify whether this is true. df by dx tilde j. Okay. Right, and then the proper formula here. Okay, so this is df by dx tilde. This is df by dx. So that means that should be the thing that connects those two expressions if it's a vector field. Okay, so it's let me make sure I get the indices in the right place. Not that it really matters because the formula is wrong. Okay, now you look at this formula and it's just got problems written all over it. Okay. All right. So J is a subscript here. J is a superscript there. K is a subscript and the subscript, and I'm summing over it in this expression. Okay. And all right, so there's the summation convention is definitely failing here. So that already alerts me that either there's a problem with the summation convention, or there's a problem with the definition of this supposed vector field. Of course, it's the second thing. The summation convention, when subjected to standard use, does not have any problems. Okay. Another thing which kind of triggers your senses that there's something wrong here is that I have an x tilde on the bottom here, and it's on the top here. And similarly, so this one kind of matches up okay. All right. And that is kind of an indication that something's wrong also. Okay, so here I'm differentiating with respect to x tilde, and here I'm differentiating with respect to x, and that's kind of it's not a robust indication that something's wrong, but it's an indication that something might be not quite right. Okay, this formula is nonsense. So it's nonsense for two reasons. So it's nonsense for just all the reasons that I just gave. First, the summation convention is failing in this expression. And again, that could be a problem with the summation convention. But there's a more rigorous reason why that expression is nonsense. And that is that we know what this is, right? We know just by the chain rule, we know what the proper expression for that is, because you're just taking a function f, which is a function of x tilde, by virtue of being a function of x, which is a function of x tilde, right? So it's, f is obtained in the two different sets of coordinates by the composition of with the overlap map. And so we know what this is by just the chain rule. Okay, so second, by the chain rule, okay, what do I know is true? Well, I know that df by dx tilde j, okay? And so I'm just going to use the chain rule to evaluate this expression. So it's going to be dx k by dx tilde j df by dx k, right? And so actually, sorry, maybe let me write it maybe the way you would write it. It's going to be equivalent, but just it sort of looks more natural maybe the first time you see it. If I want to differentiate f with respect to x tilde, I'm going to use the fact that f is a function of x tilde, which is a function of x. Okay, and I'm going to use the chain rule. So it's going to be df by dxk dxk by dx x tilde j. Okay, so that's what the chain rule normally looks like. All right, and but the way I often will write these things is I'll put the this is kind of a coefficient in front of that, so reverse the order of these things. Okay, of course, the two things are the same, but it's just it's an aesthetic choice. All right, and this are not equal, right? Okay, so this formula is wrong for multiple reasons. One, it's wrong because it's the kind of lame reason that it fails the sort of to pass the summation convention rules. And more importantly, it's wrong because, well, it's wrong because we know what the right formula for that is, and it's this thing here. Okay, so what do you conclude from that? Okay. The conclusion is that your definition of grad f does not make sense. The conclusion is that there is no vector field grad f with the defining property above. Okay, and by that I mean precisely that my definition was that in any set of coordinates, the components of this vector field grad f are these ones. Okay, there is no vector field with that property. Okay, now, okay, so this kind of leaves you at an impasse. What should you do now? Okay, well, you can just give up on grad f and say, well, I guess I don't get to use the expression df by dx because it apparently has no meaning. Okay, but that's not true. It has a meaning, but it's just not a vector field. Okay? So the right question to ask yourself at this point okay, so it's not a vector field, and the answer is that it's a covector field. Okay, and that's what we'll start talking about next time. Okay, so I will stop our recording.